you. I hope you love science because that's what we do here. There are two kinds of science, and now we're at the other end of the telescope studying quantum mechanics. Because of the nature of light propagation, it is a very good idea to understand the photon, and it's the photon that gave us the idea of quantum mechanics way back in the first decade of the 20th century. But the story really began a little bit before the photon with Max Planck. You know about the quantum packet of energy that he discovered that opened up the quantum era, although it actually took quite a bit of time. The Schrödinger equation, and there are some others, the Dirac equation, and there are at least two others. These are solutions to a very difficult problem that is posed to science because of the data we get from subatomic particle physics, which seems a far cry from the quasars and galaxies and these interacting galaxies, supermassive black holes. Oh my goodness, yes, we're going to get into that, absolutely. The Big Bang, that's the subject that's been on everyone's tongue for decades and decades now. It's grown kind of stale. The Big Bang is no longer nearly as exciting as it used to be to the public, although there's no other theory. Although one never knows, and in fact one could say there have been other theories. Certainly there was Sir Fred Hoyle's theory, but that died out in the 1960s with the discovery of the glow from the edge proving the Big Bang. There's no way they could possibly be wrong now, they think. And we, of course, know that that's rather silly. However, it's a good idea not to rock the boat too much until one understands why this theory has dominated for so long. It is the theory of the universe at this time, essentially because there is no clear, better competitor. That's not really the nature of the criticism against the theory. I've gone back and forth over the decades because I've never been particularly involved with science until 15 years ago when my wife died, and I've been taking up science ever since because it's kept me sane to some degree. That's been a most rewarding occupation, but astronomy does lead into the other sciences. So we're going to cover just a few of the things that I've been covering in 600 video presentations, over 500 of which are out on YouTube now, although I've consigned about half of them to the private sector because it took me about a year to ramp up to any level of competence doing this kind of presentation. Today I'd like to show you some information that I think will guide us as we proceed down our current path. In science, you do need to be specific about your goals, and that does mean concentration. It's not just geology, biology, or chemistry. In fact, on this page, as you'll see, it begins with the philosophy of science, but below that, the 7 cosmic units. That's really what I began to show because my original goal in making these presentations was to expose a wider audience to the realities of the universe that don't really have very much to do with theories of gravity or quantum mechanics, but simply looking at the most beautiful things that the human eye has ever seen. Now, of course, this is the beauty pageant contest. If you included gems and flowers and women and wine, there's all kinds of bests. But when it comes to grandeur, just sheer size, nothing beats the galaxies. And that's how I got into astronomy and, in fact, how I got into science. So let's proceed down our current path. This is astronomy, but we're now studying, really, geometry and mathematics. And yesterday we went all the way back to Euclid. Well, you can't do much better than to begin with Euclid. So we did so and found out what he said about the point. The very first thing he said in his famous Elements. Abraham Lincoln, I just found out recently, memorized parts of it. In any case, it's been revered for literally millennia. So it's very important to understand that this is the basis of science that is currently reigning. It really has never changed. It is the line. And that was his second statement. We covered Euclid because of his definition of the line. And the reason he began with a point instead of a line is because he had a definite idea about what the line was. And it is made of points. Now, he was not into number theory, but it turns out that this, just winding 2,500 years to the present age, John Horton Conway, one of my teachers, along with Fritz Zwicky, Halton Arp, and a few others, he discovered the definition of the linear number. And he discovered it in terms of a geometry, actually a binary tree since this is numbers, but it is describing the line. That is the number line. So 0 is at the center. I've dealt with that quite extensively, and that's a very important number. What I discovered in 2022 is there is a way to use the other identity number. There are two identity numbers, but the number 1, where we get uni, the number 1 is the multiplicative identity, and it turns out that for the longest time we've overlooked the fact that our fractional number system embodies the concept of this identity number. For instance, 2 over 1 reduces to the linear number 2. And from this we get the reciprocal 1 over 2. This is how we use fractions. They're proportional numbers, and that is the correct term for those numbers. They're two-component numbers, and a good example of that is light speed, which is given as one number, but if you look up the units, that speed implies two things. Velocity is distance over time. That's space over time, by the way, and that's why light speed is so important in relativity. It is the definition of a numeric correlation between our units for space and our unit for time. Now, Albert Einstein taught us that we now need to consider time as a real thing because he mixed it with space and showed that that could be done. That's called the Einstein field equation. Relativity is its general name, although there's a special version of that. On this page, what we're covering is basically 2 years of presentations. So the result of that is in the second group called the 7 cosmic units. But I just want to read this through and then we're going to go on to the next page. So the philosophy of science has several contexts. There are 2 aspects to a human being. And the only reason I bring this up is that it greatly simplifies a lot of problems that just a typical human faces, but scientists face some extra problems as well in just trying to come to grips with what science knows as well as what humanity is doing. Because we always have to do both in some sense. So I call that the human equation. It's quite simple. We have 2 subsystems as humans. One is emotional. Most of our lives, including the first part of our lives exclusively, is emotional. It's not logical. The other side is rational logic. And that's the basis of science, is rational logic. So those are the 2 subsystems that we have to correlate. They don't really mix outside of a single human being. So it's a matter of individuality. So that's the human equation. I believe in perspective above all. But we're human, so we do want to be good diplomats, both for our own sake and for the sake of those that we're trying to reach and influence with the truth. In science, we're all scientists, if we want to be. It is a conscious decision to prefer logic to emotion, and it comes at a cost. It's important to know why we're studying quantum mechanics, and I tried to explain that at the beginning. It's in context of astronomy. Well, why are we studying astronomy? So then the 7 cosmic units, luminous objects that statistically fill the universe. So there's the stellar, nebulae, which we now call galaxies. That is a galaxy. It's involved in an interaction with another galaxy that you cannot see. It's off the screen. But that is a real photograph. Beware. Be very aware of artists' renderings. So that is the 2nd cosmic unit. Edwin Powell Hubble devised what is called the tuning fork, the elliptical and the spiral. This is a spiral, although it's distorted. Ellipticals are basically spherical, but scientists prefer to say elliptical instead of spherical. That's fine. There is also a special kind of spiral called a bar spiral. You may have heard of galaxy clusters. Here's a galaxy cluster. I think that this is one of the most beautiful things that I've ever seen. Now, this is what I warned you against, is, for instance, this. That's an artist's rendering. And it's okay to look at them. I know what I'm looking at, but these things do not exist as they're drawn. This one here, you can see there's a set of 6 tiny photographs. Those are quasars. As for the accretion disk, that does not exist. So that's 4 cosmic units. Superclusters are essentially spherical, but they form one giant thing. And the nexal points are the giant parts, the parts that were first identified as superclusters, are actually connected to other superclusters. And the superclusters are concentrations of clusters. We have the star, and then the galaxy. And the galaxy, of course, is emitting starlight, but it is a separate object made of stars. Then the cluster of galaxies, that's the third cosmic unit, essentially discovered by several men, but Fritz Zwicky generally gets credit for that. Well, at least in my mind he does. He's the one who proved that they're separate from each other. He used a special mathematical formula. He knew Einstein. He was a top-notch mathematician. And he used the virial theorem, V-I-R-I-A-L, to prove that clusters of galaxies are separated from each other. They're not woven together. They're separate. But they form superclusters, which are woven together. So the star is 1, galaxy is number 2, cluster is number 3, supercluster is number 4. I call those the strati. And the entire web, I call that the Cirri. That's 5. So there are 2 more. And these are not commonly identified as such because of the current cosmological model. And I don't mean to impugn it. I'm sure this is all, it's not like there's some kind of conspiracy. But once you've glommed onto a model, it's very easy to look away from, I'll just say, avenues that you could explore. And I could go on about that. I have in many lectures because I'm very sensitive to this issue of discovery science and astronomy. There's a certain part of astronomy that's suppressed. It's not, I don't believe, conscious. It's just ignored. And this is the part that I'm trying to expose to view, is that we have a wealth of incredible information that's absolutely fascinating. And instead of looking in the direction of the structure of the universe and talking about these cosmic units, for instance, how often do you get a seminar on galaxies, clusters, and superclusters? Well, they're absolutely fascinating. These things collide, or they interact, actually. Galaxies do, but so do clusters. They actually have been photographed with X-ray photography showing how they pass through. They collide. They have gas and all kinds of things. The cluster is a thing, and there's not much information yet in astrophysics on how these things form. Of course, the cosmological model dictates what they just assume must be the way they form, but it is very contrary data. The models don't match the data, and they're very hung up on accretion, congealing because of gravity. It's reasonable, but it's very, very one-sided because there's so much that just cannot be explained by this contraction. Things are exploding in this universe all over the place. We don't really need a big bang. There are big bangs going on everywhere. But that's to get ahead of the game. I'd like to turn to the second page so we can close this off in a reasonable amount of time. We're now drilling down to what you and I are dealing with and will be over the upcoming days. This is the only time I'm ever going to do this, but I thought it was the right time to just bracket where we're at. Now, this information you see here, it's quite jam-packed, I think, so I'm just going to go through it quickly. The Panther family, I'm a fanciful person. I feel lighthearted about issues which could become quite serious because I'm furious, absolutely furious, at the name of black hole and Big Bang. I'm very sensitive to these things. So this is a personal issue. But if they can do it, I can do it. Panther. So the supermassive black hole, I call one of the members of the Panther family. You don't have to go along with that, but that's what I'm going to do. The quasar is a panther. The supermassive black hole is a panther. There are various kinds of panthers. The thing that is called a supermassive black hole, which it has been claimed that has been photographed, that is a lie. You cannot photograph a supermassive black hole. It's not because it emits no light. It's because the object is not what they think it is. Not at all. And I know that for a fact. Believe it or not, that insight comes directly from the spherical geometry that I discovered. But we're going to cover that. I've already covered it many, many times over the past 500 lectures. But I don't ever expect anybody to go back and watch my lectures. If I can't summarize my work, I'm not a real scientist. So I'm going to be doing that, but not immediately. We're currently involved with quantum mechanics and light propagation and the Bohr atom and the nature of the electron and proton and centrifugal force and centripetal force, the force balance system that Bošković discovered that actually is capable of extending space-time to much more. It can be made better. Space-time is in slightly inaccurate formulation. Space-time is real, but not the way Einstein formulated it. This may sound revolutionary. Get used to that because there's a lot more of that. None of this is fanciful or in any way off the wall. It's all entirely grounded in absolutely well-known, accredited work. So I'm not a crank, and don't ever make that mistake. No, this is the real thing. So that's the Panther series. Now, subatomic structure and mechanics, this has to do with my spherical geometry, which reinterprets subatomic physics. And it's largely due to the work of Bošković that we're getting down there. To that, you'll see it in the middle of the page, and his book Theoria, which I read. But the discovery of spheric geometry was accompanied with the discovery that it has a number system, and it actually is our multiplicative divisional, is what we've always been using. It's actually our fractional number system is a proportional number system. That's a fact. That's not, the Greeks knew that, and it's well known. No mathematician would disagree with that. Fractions are proportional numbers. We say division, but that's really inaccurate. They're proportions, and that is accurate. And the inverse of proportionality is multiplication. It's the equivalent of subtraction. Proportionality is the system that the universe uses. Max Planck discovered that, and his name isn't in here, but neither is Einstein's, although Einstein's virtually is, and so is Planck's. So that's the proportional number system which I discovered. In itself a major discovery. It goes all the way down to the operator system of basic mathematics, that our linear number system is exclusively identified with the line. That means it's exclusively identified with add. And we've been trying to use multiplication and division on the line. And that's why we have the quantum mechanical paradox. And it's also why we have so many mistakes about the black hole and the Big Bang and quasars. It runs right through science because we're stuck with linear numbers, and I've proved that those are inadequate, and Bošković proved the same thing. So that's where we're going. Continuing down, I have symbols for centripetal and centrifugal force. This uses the very well-known principle in spherical space, although you very rarely hear anybody talk about spherical space. Centripetal force is gravity. That's what gravity is. You shouldn't even call it gravity. You should call it centripetal force. Of course, we're going to call it gravity because that's the macroscale version of centripetal force. But can you think of any other centripetal forces? Well, what is a centripetal force? It's something that draws toward it. It's pulling towards its own center, and it has to be a center. That's well known. That's called magnetism in the electrodynamic context. In macrospace, it's called gravity. But in subatomic particle physics, it's actually centripetal force is the only right name. And physics has not caught up with the insight of Bošković, and now I know that Bošković is right. And so physics is going to have to catch up. So that's why I'm making these presentations, in part for that reason, that the geometry that I discovered validates Bošković's now being resurrected work. And I'll be talking about Bošković a lot, and I'm going to show you where two infinities meet in the Bošković force curve inside the atom that fully explains the electronic balance inside the system, and it also explains the strong force. That's why there are hadron colliders. They're not to cure cancer, and they're not to help humans. They think they're close, but they'll never get it. But if they know my geometry, they might. We're then going to talk about space-time, and light speed and space-time are extremely closely related. We'll talk about 4D. That's a very significant term, 4D. That D, you know what D means? It means the number of lines. They're not dimensions. I discovered what a dimension is. And the word dimension is being used incorrectly. D means number of lines. That's what D means. The number of lines in your basis system. So space-time is a 4-line system. 3 of them are orthogonal, and the 4th one is imaginary. That was brilliant on the part of Einstein, and he got it. He nailed it, but nobody's realized that he nailed it. I realized that he nailed it. Because time, as he calls it, it's not actually time. He got that wrong. But he's close. They're perpendicular. That's what orthogonal means. One of the components of energy is time, and we're going to talk about the other component of energy because that introduces us to the space that we need to see into in order to solve the quantum paradox. You will fully understand entanglement even though the physicists don't. Light is the quantum phenomenon itself. The universe can be constructed using spherical geometry to rationalize infinity. This gets rid of Cantor and Hilbert, and anybody else who's been trying to make the straight line continuous with their real numbers. A fool's errand. So the rational infinity for space-time, I'm also going to show you in the Boschkovich force curve that the 2 infinities of space and time, I'll just keep calling it that. It's not actually time, but they're perpendicular. And that can be proved geometrically. Okay, and then, right at the bottom of the page there, the quantum paradox complex. I've studied under Scott Aronson. I know quantum computing, and there's a lot to be said for quantum computing, but actually, it's a dead end the way they're doing it. And by summer, we'll be into hyperspheric space. Hyperspheric space is actually space-time, time-space, and you're going to love it. This is the best time I've had in my whole life, and I know it's going to continue. I'm going to be doing this for as long as I can, and I'm going to try to get up to the Creator's throne to fall down and just worship Him for all the goodness He's shown to me. That's what I feel about astronomy and the universe. So, as Buzz Lightyear says, to infinity and beyond. Keep looking up. That's where you're going to get your real answers. God bless you. We'll be talking with you soon. There will be a posting at Anagalactic.Space sometime this week. Keep looking up.